Hello everyone, this is Dr. Webb. In this video we're going to talk about arc length, which often sometimes is taught, somewhere in either Calc 1 or Calc 2, but I would think more times than not it's often skipped because it makes an awful lot more sense and it's a fair bit easier to do once you have vector functions. So let's do arc length through vector functions. So let's just recall that if we have r of t is drawing out a curve, then it's the vector function itself, it is the position vector, right? So if we have our axes, here is our curve. What r of t does is it points from the origin to points on the curve. So r of t1, r of t2. The derivative of this vector function is going to be going tangent to the curve. So that would be r prime of t1, r prime of t2. If we're out over here, r prime of t3 would go tangent that way. And then we talked about if you then, if r prime of t, this is giving a tangent vector, but really it's the velocity vector, well then its magnitude, the magnitude of velocity is speed. Right? Well, speed, if you think back from Calc 1, speed, we usually think about speed as being the derivative of distance traveled in terms of time. Right? Speed times time equals distance. And so, if you think about the derivative of distance, that's going to give you speed. Well, this means that if speed is the derivative of distance, what do you get when you integrate speed? That's going to give you the total distance traveled. Okay, and so this is a very hand-wavy way of explaining the formula you're going to see for arc length. I can give you a little bit more geometric and slightly less hand-wavy, but morally correct version. And so the idea is that if you have a curve, and let's say this is r of t naught, and then you add delta t to that. Let's say that gives you r t naught plus delta t. Well, if you just take the difference between these two vectors, that difference, the length of that difference is going to be very close to the arc length between those 2 points. Right? You can see that it's between those 2 points, it's almost a line, so if you take a straight line between them, that's going to be very close. So r of t plus delta t, I guess I had t naught plus delta t, minus r of t naught, that's roughly the length between them. Right? On the other hand, you can see this length is roughly the tangent to the curve. Right? And so we also can use the fact that if I did r of t naught plus delta t minus r of t naught and divided that by delta t, well, this is now looking very much like the formula for derivative. And if delta t is small enough, this is going to be approximately just about the value of the derivative at r prime of t naught. Okay. And so then I can multiply both sides of this equation of this approximation by delta t. And so then we get that this distance write that back in. That r of t naught plus delta t minus r of t naught is about equal to the velocity vector at t naught times delta t. And so then when I take the magnitudes, delta t is just a scalar. It's just representing a real number. So I can pull it out. And so the magnitude of r prime of t times delta t is going to give me about the distance between the 2 points. And that's about the arc length. And so then if I want to do this over and over again, do it from there to there, 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 up until some other point. Say this is where, well, at least use the right notation. R of T1, well, we could then do a Riemann sum. It would be adding up a bunch of segments that look like this, and they're all about equal to that. And so we get that the total arc length is going to be about this sum of these r prime of t whatever times delta t, and then that should be approximately, and then how do we make it equal to the whole thing? Well, we go through the whole Riemann sum thing, take the limit as number of cuts go forever, short things go on, and we end up with the integral of the derivative of the magnitude of the derivative. So write that up nice. Right, so if we have a vector function r of t, if we integrate the magnitude of the derivative, so the speed function, that's going to give us the arc length of the curve between the points at t0 and t1 of the curve. Okay. So this is a very nice looking formula, and it looks very pretty, but we have to remember that this magnitude, it's taking the square root of a sum of things squared. And so that, very quickly inside of an integral can actually get pretty ugly. So while the formula is very pretty, actually calculating arc lengths exactly can actually be pretty tough. But here's an example that'll work out pretty nicely. So we're going to try and find the arc length of the curve t cosine t sine of t from the point 0, 1, 0 to pi over 2, 0, 1, 0. And so just a quick picture. I think that we looked at this example before in an earlier video. And so it's starting off at this point 0, 1, 0. And then because we have y squared plus z squared here, since they're sine and cosine, y squared plus z squared equals 1. So this is all happening this is all being cut along the cylinder that goes down the x-axis. And the x part is actually curving out the edge of this, right? And so this is going from the point 0, 1, 0, and that's going to be at pi over 2, 0, 1. So for the formula, we need to know what the values of t are for both of these. But since the x component is just t, the x component of the first point tells me we're talking about t equals 0. Let's write that correctly. And the x component of the second one is saying that we're using t of pi over 2. Okay. And so the integral that we're working out is 0 to pi over 2 of magnitude of r prime dt. We need to figure out what r prime is. but that's just taking out, that's just doing the derivative component by component. So r prime of t is going to be derivative of t is 1. Derivative of cosine is minus sine. And derivative of sine is cosine. Right. And so then when we take the magnitude, 0 over pi over 2 of 1 squared is 1, plus minus sine squared is going to be sine squared. Cosine squared is cosine squared. All of this times dt. Now we have a sine squared plus a cosine squared here. So that's going to equal 1. And so I have 1 plus 1 inside the square root. I get that my magnitude here is square root of 2. So we're just integrating square root of 2 from 0 to pi over 2. And so that's going to be square root of 2 from 0 to pi over 2, which is square root of 2 pi over 2. And that's our answer. Okay. So this one was very simple and straightforward to do. And main reason it was simple is because this magnitude ended up being a constant. That tends not to happen when you parameterize things. Circles, it happens more often than other places. But other places it often doesn't work out nearly that nicely. And so you can even take sort of fairly simple curves like parabolas, and it suddenly becomes very difficult to calculate arc lengths. Okay, so this is a fact I think we talked about in the last video, that if you have a vector function and then you take some scalar function, a real valued function, plug that into the vector function, it's going to draw out the same curve, but it's going to draw it out at a different speed. Right? And so if we plug in, if we compose some scalar function into the vector function, then we're just getting a different parameterization of the same curve. Right? Well, so this brings us to what's a special parameterization, which is called the arc length parameterization. We usually use S to talk about arc length. And so if we write a vector function as r of s, we're usually saying that it's in the arc length parameterization. And what that means is something is in an arc length parameterization if whenever you want to get the arc length between 2 points on the curve, it's equal just to the distance, it's equal just to the difference between the s values, right? And so this is another way of saying that the speed of r of s is a constant 1. Okay, so how can we justify this? Okay, so we just saw the arc length formula before. Right? And so this is saying that if we're in the arc length parameterization, arc length equals, well, if we're doing it between s equals 0 and s equals 1, that'd be the integral from s equals 0 to s equals 1 of the magnitude of r prime of s ds. And we're given that this is equal to s1 minus s naught. Well, I can think of another integral that would give me s1 minus s naught. And that would be just integrating s0 of s naught of 1 ds. You know, you can double check. If you integrate 1, you would just get s, plugging in s1 minus s naught, that'd give you s1 minus s naught, right? And so if for any value of S0 and S1, you get that these are exactly the same, the only conclusion has to be that they have to be equal to each other if they always integrate to the same value, no matter what the bounds are. Okay. So if you're given any old parameterization of the curve, how can you find in one of these special arc length parameterizations? Right. Okay, so this is a process we're going to do it. So first thing we're going to do is we're going to pick a reference point t0. Okay, and this is what's going to be the lower bound of our integral is going to be, and this is going to correspond to the point where s equals 0. So this is just sort of a starting point from where we're going to start calculating arc length from. Okay. The next thing we're going to do is we're going to actually calculate the arc length in terms of t. So if you notice, we have our reference point right here, and this should be r prime of t. So we have our reference point. If we integrate r prime of, right, we're using tau because we're putting t into the upper bound, so t, this is our parameter t. So to use good mathematical grammar, I've got to use another variable inside the integral. So when we integrate r prime, the magnitude of r prime from t naught to t, that's going to give us the arc length from t naught to t of the curve. And if we let this parameter change, then that's going to give us a function. So we get s of t here. Well, so now we have arc length as a function of our parameter t. But what we really want is the inverse of this. What we really want is a way to write what t is as a function of the arc length, right? Because we want to replace t in the parameterization of r, and we want to replace it with something that's going to give us the arc length parameterization, right? And so if we have s is equal to some function of t, well, how do we invert it? Well, we want t to be a function of s, right? Well, how do we get t to be a function of s? Well, we're going to invert this function, as we were saying. So we're going to start off with s of t, solve for t in terms of s, and then we're going to replace t and r of t with that function, and that's going to give us the arc length parameterization. Okay, so this was a bit abstract. So let's actually go through with what we did before. Let's go back to the problem we did before. And so if you recall, we already figured out that the magnitude of r prime is always square root of 2 here. And so then s, our arc length, let's not even put in the of t. Let's just call it our arc length. Let's use our reference point is going to be 0. So this is going to be the integral from 0 to t, a square root of t, d tau. Got to use something different than t. And so integrating a constant, this is going to be tau square root of 2, going from 0 to t, which is just going to be s is equal to t times the square root of 2. Right, so I have s is equal to some function of t, but I want it the other way. And so s over square root of 2 is going to equal t. Okay. So now we have the arc length. We've written our parameter t as a function of the arc length. And so this means that the arc length parameterization is going to be plugging s over square root of 2n for t up here. And so that's just going to be, let's write it down here, s over square root of 2 cosine of s over square root of 2 sine of s over square root of 2. And there you have it. Okay. So as I said, for this was a really straightforward example. This one is pretty nice because the speed already was a constant, so going from a constant down to 1, you're just dividing by the right amount. Quite often that is not nearly this nice. So as a brief example, if we do something simple like t comma t squared. So this is not going to be too bad, but this is just this is going to go along the parabola y equals x squared. Well, the derivative of this is 1 comma 2t. And so then the magnitude, the speed function for this is going to be square root of 1 plus 4t squared. And so then if we want the arc length between any 2 points, or we want this arc length parameterization, this arc length, say if we use reference point 0, we'd be integrating from 0 to t of 1 plus 4 tau squared d tau. Well, this is not a simple integral to do. You'd either have to do something like integration by parts or use a trig substitution with something like tangent or secant to get a handle on this. So this is a very familiar curve, and already this is a pretty ugly integral for arc length. Okay, so that's what I've got for this video. I will see you again soon.